Hi there and welcome back. In this video we're going to talk about binary search. Let's start by looking at the list that we had in the last video. Here we've got a bunch of numbers, and like you know, if we want to find a specific number, like 90, which is there near the end, we have to sort of start at the beginning and go through each number until we get to 90. However, there are ways to be more efficient about searching for a specific number. If we sort the list first, which there are various ways of sorting, some of them are faster than others, and I'll teach you how to sort a list later on. But if you sort the list, now it's much easier to find stuff. Just in the same way that if you have a dictionary, you don't start at A and end at Z. For example, if you're looking for a xylophone, you'd sort of start near the end because you'd know that it's ordered alphabetically. When your lists and your collections are ordered, it becomes a lot easier to find things. However, important to say, just because the list is ordered doesn't mean that automatically your searches are going to be more efficient or the complexity of them is going to be less. Finding sequentially is still ON. If you want to find 90, you still have to start at the beginning and go through each element if you're finding sequentially. So, let's instead find in a different way. Let's explore a different way of searching and finding an element that isn't sequential. Remember, one important aspect about lists is that you can access any one element. It doesn't have to be the first element. So you can access the last element or an element in the middle if you want. So let's look for 90 with a slightly different algorithm. Instead of starting in the first element, we're going to start in the middle element. So in the middle element in this list is 38. That is index number 10. So in this algorithm, what we're going to do is we're going to ask the question, is 90 greater than 38? So again, we're looking for 90, and we're just asking ourselves, is 90 greater than 38? And the answer is yes. So we're going to discard all lower values, all the values that are lower or equal to 38, we're going to discard, and we're only going to keep the values that are greater than 38. Why? Because we know that the list is ordered, so any value that is to the left is going to be less than the value we're looking for, so we don't have to worry about them. We don't even have to search. So let's grey them out to signal that we've forgotten about those values, we've eliminated them, we're not going to search there, and then we're going to move over to the next middle element of what's left. Notice that integer division doesn't round up. So here we end up with 4 elements on the left and 5 elements on the right, which is a slight problem in this case. It's going to make things a bit slower for us. But nonetheless, we end up in 59. So again, we ask us the same question. Is 90 greater than 59? And the answer is yes. So we discard again all lower values. So 59 and down we can discard because we know that 90 is not in any of those. And again, we look for 90 by moving to the next middle element of what's left. Now we're at 717. Again, you ask yourself the same question. Is 90 greater than 717? The answer this time is no. It's less than 717. So we're going to discard all the right values, all the higher values, we're going to discard them. Notice how now we've got 2 values left, and the next jump takes us to 90, because once again we don't round up, so 2 divided by 2 is 1, so that brings us to this index here, and we ask ourselves the question again, is 90 equal to 90? And we say yes, so we found it. Now we found 90, and it only took us 4 jumps. If we had done this sequentially, it would have taken us 17 jumps. So I think that this is much faster. And it just so happens that the log 2 of 21, which is the number of elements in this list, is equal to 4.39. which means that this type of search we've done, which is called a binary search, is actually O of log 2n, which means up to 5 jumps. And here we took 4 jumps. If we had been looking for 95, it would have taken us 5 jumps. Now, what we've looked here is a binary search. A binary search works by, at every jump, making a decision that leaves you one of 2 choices. Go right or go left. Go right or go left. This binary search means that at every jump, you're getting rid of half, or approximately half, of the elements remaining, which is why this is a logarithmic complexity. The complexity is O of log 2n, which is much better than On. Indeed, it is an exponential, or inverse exponential complexity, which is much faster. This type of search is one of many various search algorithms that I encourage you to look into if you are interested. And if not, just know that there are ways of improving on existing algorithms, like sequential search can be improved on by binary search. And as such, this performance type subject of computing is a pretty important area. Now, in the next few videos, we're going to look at how we can perform binary search on a slightly different structure that isn't a list. And see you on the next video.